Hi everyone. Today I'll present, basically me and Harald over there will present our adventures in functional programming and high performance graphics. It's actually kind of an alien talk here since we're not at all web developers, or at least we didn't used to be web developers, and we're also supported by Attila here. And first of all, I'd like to give you a little background on who we are and where we come from. We're all working at the VRWIS Research Center in Vienna, which is a research center close to the university, which is basically concerned with computer graphics and visualization of things. And recently we founded a startup called Artworks. As the name suggests, we're the maintainers of Artworks, so to speak, which focuses on providing high-performance graphic solutions for companies in a real-world application setting, and less in a scientific setting like VRWIS does. We have a long history with functional programming and are rather enthusiastic about it. And yeah, as I already mentioned, we're the main contributors or maintainers of the entire aardvark platform, which we will show you in this talk. The whole thing is open source, since I'll come to that, I can't remember. And it's basically a rendering engine plus an ecosystem providing tools people need for creating rendering related projects. So what is aardvark? It's actually quite old. We started development in about 2006 at VRWIS. It was all written in C# back then. And the focus was to provide a platform for our research and industry projects concerned with rendering 3D scenes or 3D data. And the focus always was ease of use and extensibility of the whole system, because especially research projects often come up with different requirements on what a rendering engine must do or has to do in order to fulfill our needs. Then a long time after that, in about 2014, mostly the entire system was rewritten in F#, with all the ideas we had from our experience, with several conceptual shifts in the whole engine development. And yeah, the whole thing is open source since 2015, and we have a functional first API, which Harald will later show you, that is quite similar to Elmish or the original Elm, which we have about since 2017. And aardvark powers lots of research and industry projects, although the open source community is still rather small. And yeah, I'll start. Yeah, these are some projects. Basically, this is a lighting simulation done with our system. It aids lighting designers with designing building illumination. And this is one of the things. Then we have also very visualization-centric and simulation-centered applications. And recently, this is a project with ESA, the ExaMars project. And as you see here, the focus of our programs kind of shifted. It's more an interaction. It's an interaction, heavy interaction system basically. Users annotate stuff. Users interact with 3D data instead of just looking at simulation results. So first of all, what do we call a rendering engine, since the term is heavily overloaded in the world? Basically, what we call a rendering engine is the thing browsers also call a rendering engine. Basically, as you see here, everyone knows that you have HTML code and you have some kind of magic that turns that into pictures on your screen. And as changes flow into the original scene representation or the original DOM tree, the views get updated. This is basically mostly done in the classic web with JavaScript or Elm. And on the bottom, you see what we'd like to do. We have also a scene description. We call it scene graph. It's a very common concept in computer graphics. And then we have our rendering engine, which turns this scene graph into images. Obviously, this image is not this scene graph, but you get the idea. So how do we do that? Or a little look in the box. And I'd like to start with something rather alienating. It's not related to rendering at all. It's basically our incremental system. And I'd like to explain a little about it because it's one of the core concepts of the entire engine, or drives lots of our ideas. And basically, at the first glance, it's very similar to what RX or other reactive systems do. It's basically concerned with propagating changes in the program. And what is different to RX, it's actually a dynamic dependency graph. It's not, it doesn't represent streams of events or something. It represents values, changeable values, values that may be affected by some input changes. And yeah, on the implementation side, it's a push-pull based system, which is basically inspired by Adepton. It's a paper from, I don't remember when, it's rather old, 2014. And I'll just explain the example here on the right, and maybe that gives you a sense of what we mean. So basically, on the top we see we're creating, basically this here is creating a changeable cell. We call those mod for historical reasons. And basically we initialize a cell that contains the integer 5 here. And as you see, we have combinators here. This is just a simple function that takes a modifiable value of an integer as input and produces a modifiable value as output. Basically, just like lists or just like reactive, you could also do that with RX, just mapping the value and multiplying it with 10 or something. And in the next example here, this is one of the main differences between what event-driven systems and our systems do, because you have a real dynamism here. You can, basically, this says whenever A changes, I need to evaluate this here, and as you see, B also is a changeable cell, which means I can switch between depending on B and not depending on B, and I never have the problem that RX basically has. RX doesn't have a latest value for B, because B is an event stream and B is not a value. And in our system, you can get the latest value for B. B kind of promises that you will always get the value from it. And yeah, this is also one of the concepts. We have constant nodes. In order to make the system composable, we kind of need a leaf entry or a non-changeable entry somewhere. And yeah, the test code here below basically takes the changeable, maps it with the mapping function defined here in the simple. And obviously, force extracts the current value of the cell, which is actually quite unsafe thing because you don't know when it changes again. But this is just for illustration purposes. You extract the current value, and obviously we have 5 times 10 is obviously 50. And also, what the system supports, you have those transactions, and those transactions can feed new values into changeable inputs. So basically, if we change the value to 10, the output obviously gets 100, and the system takes care of all the necessary re-execution. So basically, that's just this lambda here above will get re-executed. And
where have you referred to dynamic? Sorry.
Pardon?
If you don't mind me asking a question, where have you used the dynamic function you've defined?
I didn't use it here. It's just for illustration. We'll see that later on. But this is just to get the. This is basically the main point where it differs from classical publish-subscribe systems. But yeah, basically this imod cell here would be sufficient to express everything. I could just stuff it with immutable sets and update those. But as it turns out, for sets, lists, maps, and all those collection data structures, there are more efficient implementations possible that actually just operate on the changed elements and not all elements of the list. So we have special types for those. We call them a set, a list, and a map. A stands for adaptive, and imod should actually be called aref, but it isn't for historical reasons. And yeah. So this system is the heart of our whole rendering API, basically, and I'll show you how we use it in our scene descriptions. basically the entire scene description we have is takes incremental input values at any position. So if you have, you could, for example, have an adaptive set of some scene descriptions, and inside the scene you can use it via just via combinators that actually take care of how things are added, things are removed, or things change. And there's always the constant parts like the sphere here. So of list basically takes the sphere and the dynamic set of objects and just groups them together. We have attributes in our scene graph, which are basically similar to style properties in HTML or something. We can always fill in constants, and we can also fill in dynamic computations that depend on other things. We opted for explicitly tracking where changeable things are and where not, as opposed to the classical HTML DOM tree, which basically allows you to modify anything using JavaScript later on. You just define a tree, and JavaScript can just modify any entry. But that takes away from us, that steals us kind of the ability to optimize things in our rendering engine. And so we opted for annotating constant cells explicitly, which allows us to heavily optimize the rendering process of the thing. Yeah, what I forgot is we basically take that scene description and turn it into we kind of compile an executable program out of that. That can be executed on the graphics hardware. And whenever the input changes, whenever the user changes or adds an object or something, just the incremental change is propagated through, way through to the backend. So the backend just takes care of allocating resources on the GPU or adding and removing stuff, which is rather powerful. And yeah, therefore we avoid the classical scenario in rendering engines of retraversing the scene representation all the time when something changes. Yeah, so all of this is a bit dry. Yeah.
So that last part is only applicable to interactive applications, right? So they're not
yeah,
there's like some.
You could also have something like an animation or something that basically always changes values. Yeah.
So you said in your compilation process, do you take a scene graph
Yeah.
value? Do you take the SG value, or do you take quotation of the thing?
No, we basically take the scene graph and actually we turn it into an adaptive set of renderable objects. It's a one-time traversal that actually flattens out the entire structure.
Okay.
And
you can kind of flatten out the static part of the structure. But
no, also the dynamic part of the structure.
Dynamic bits left of some kind?
Yeah, no, it's all dynamic. In the end, you end up with an incremental set of things you need to render. Yeah. We're in we kind of are in luck because we have rendering only cares about objects being rendered. There is only one kind of leaf, which is in our tree. It's basically render the thing.
But you said you could do a fair static resource allocation and so on.
Yeah, it helps a lot because we know the static parts of our, there are static parts and there are dynamic parts of our scene.
Okay.
And all those...
So for a scene graph like the one you've got there, some bits of it are...
Yeah, for example, the sphere here, is totally static. It will always exist. You can't delete it from the scene.
I see.
But things in here can be deleted, so we can do some trickery in our backend. But I'll actually just show you a demo here. This is actually not our rendering engine. This is a very, very early prototype done with Fable that basically runs on WebGL. So we have a little ASCII art here. And yeah, basically we can just create boxes, for example, for all our characters. We look up the character code and say, okay, let's render a box at the position we'd like to. And what we have here is also textures. We have the Fable logo and the F# logo here. And basically, based on the character above here, we decide which texture to use, but for this particular cube, the texture is actually a constant. This is one of the examples. We have conceptually, if the texture were changeable, we would actually have thousands of text or 100 of textures in here. And due to the information that the texture is actually constant for that cube, we can optimize things. The backend understands, okay, there are 50 cubes having the same texture, and we only allocate the resource once and do not have to check whether or not it changed. And yeah, we can compose that here, just creating a list for the entire text, making boxes, and yeah, for the white space characters we return nothing here, so we don't have a representation for these. And finally we end up with an image like that. The camera controller is actually hardwired here. And here's an example of what we can do, or a little dynamism in the system. We basically have a render control which represents the view on the right. And this one gives us a time. We can depend on the time, which is it's a mod of float. We can depend on it, and based on it we calculate some kind of transformation. And if we apply the transformation here, we get a simple animation that just rotates the thing around. We can obviously, for example, create a sphere here, which looks a little, yeah. So this is actually reloaded. This is not dynamism at the moment, but you get the idea. The rotation transformation is basically a computation that depends on time. So yeah, we have a system that is basically what this is it's the core of the entire thing, and it serves, or the analogy in the internet web development thing is basically this is HTML and basically a little CSS animations, if you will. So yeah, let's get back. However, in rendering engines there is one big topic that is most often avoided and is interesting for us. It's you have to write shaders. If you don't know what shaders is, don't be scared. It's actually something very simple. This slide actually illustrates how it was in about 2005, but it's just to get an idea. Basically, when you render things, you have inputs to your system, which is geometry, textures, values, or transformation values, and things like that. Then you have a programmable vertex shader, which takes care of transforming the things in order for the camera to see them. You have a hardwired rasterizer, which basically turns your triangles, lines, or whatever you'd like to render into pixels, or pixel positions. And then you have a fragment shader, which basically turns those things into colors, or whatever output you desire. Yeah, shaders are mostly used for visual effects like lighting, texturing, but there's also computation-heavy uses of shaders actually, and especially since compute shaders exist. But that's not the focus here, and yeah, shaders currently need to be specified in super low-level languages. Most of them are C-like, some are a little assembler-ish. Basically the two main languages are GLSL and HLSL, which is the GL shading language and the DirectX shading language. They need to adhere to very restrictive restrictions. You do not have allocations, you do not have recursions, you cannot define recursive types, and all those things. Furthermore, vertex and fragment shader always need to match in order for the rasterizer to work. And those languages have a real lack of abstraction mechanisms. There is really nothing that helps you to write more reusable shaders. So that was the situation we were confronted with, and we decided to improve on that. So what we came up with is called FShade. It's basically using F# quotation mechanism in order to get access to the code for our shader functions. It's realized as a full embedded DSL in F#. And yeah, one of the main ideas for simplifying shader development was to use function composition, just compose several effects one after the other and pass the inputs around. One of the main differences to just regular function composition is shaders typically take a lot of inputs and produce a lot of potential outputs. For example, if you take, you have something like a position of your triangle vertex, and you have a shader that takes care of transforming the position into the appropriate space, but it may also transform the normal, or you also have different kinds of output that need to be passed to other shaders. So basically this is a little like arrow compositions from the functional programming world, but we decided to just compose things by names because most often those things have reasonable names or a semantic meaning to them, like positions or colors and stuff like that. So I'll show you what that system can do for us. So while it starts, basically these are shaders written here in F#. We have computation expression builders, which we basically exploit them to give us the quoted code of the function here. So we get runtime access to this function, which takes a special input type. This is just a record here. As you see, those are the annotations I mentioned. Those are the real names or semantic meaning of our inputs. And these things guide the composition. So if a shader takes a position and the other one produces one, we will compose those when the shaders are composed. So basically, yeah, this is just regular F#. You see, okay, we need to multiply the position vector with some matrix and yeah, lots of other things. Yeah, there's also a fragment shader effect here, which I don't know if any of you are familiar with normal or bump mapping. It's basically a trick to make objects look more realistic. We have just a texturing, we have a specular color, we have, yeah, this one's maybe interesting. This is a lighting. And yeah, you get the idea of how those shaders look like. They're just regular F# code, which obviously comes with most of the restrictions we have in the target language. So you cannot use any recursive functions or lambdas here inside your shader. But it actually turned out that for shader programming, this is not really a hard restriction, so to speak. And yeah, I'll just show you what this does. So what we see here is just a model we have. And on the right, I think you cannot read it, but it's maybe better that no one can read it. This is actually the output code. This is GLSL shading language. And as you see, if we turn everything off, yeah, this is just a transformation with nothing else. And you see it's, yeah, there is a little boilerplate involved. You need to pass things around. You need to annotate everything. And when I turn on several things, you get the idea of what happens to that code. And regular practices or in game engines, actual people develop these things, and the problem is you often have variants. If you have, for example, you have here, if you want a low detail representation, for example, or a high detail representation for better hardware and a lower one for the others, you might just want to turn off some of the effects here in order to speed up the rendering or to use less memory or whatever. And as you see here, whenever I compose something different to it, the entire code changes. These changes are absolutely non-local. You need to define hundreds of things in order to wire everything correctly. So especially this one and this one. You see here suddenly our shader has 20 inputs instead of 3 or 4 or 5. So basically the function composition and the whole code generation idea hugely benefits shader programming, because you actually do not have, yeah, this is the empty shader. You no longer have to write 7 variants of the same thing, because you can just compose things and use it use the output code in your rendering backend. Yeah. To conclude the rendering and FShade part, F# quotations are actually super helpful for creating embedded domain-specific languages like this. Yeah, this is a little side note. Computation expression builders have a magic quote functionality which is super undocumented. Please never drop it.
The way to make that happen,
Pardon?
the way to make sure that never happens is make sure you submit a test case to the F# repository.
Okay.
Capturing that actually works the way you want it to work. Or check that there's a test case for it. But yeah, it is really undocumented. It's interesting they're using it. So you're not using reflected definition.
No, we tried that, but it doesn't. The code doesn't look that neat actually. If you just want to write a function and not a global binding to things, this way we can write inline shaders, inline in our scene graph and stuff. But yeah. What would be nice would be a possibility to kind of do some pre-processing in the F# compiler itself. Especially our shaders are heavily pre-processed, and we currently do all of that at runtime. We have caching mechanisms and everything, but it would be nice to have a possibility to pre-process those things a little in the compiler itself. And yeah, aardvark rendering and FShade basically provide a flexible and efficient toolkit for rendering and visualization stuff. It's all running on .NET Standard. Actually, the demo I showed you was running on Fable in JavaScript. Yeah, it runs on Windows and Linux, and yeah, okay, the demo is a very, very early prototype, but if you want like to look at it, it's available on the URL given. Yeah. And now Harald's going to tell you a little about our application adventures.
So what we have now is we basically have a rendering engine which is capable of rendering dynamic content. Dynamic in the sense that we have animation, time-dependent stuff. However, it's a rather limited form of dynamism. So what we found in our projects is that we moved from a visualization rendering perspective, where we have large data, we need to visualize this, we need to write shaders and all of this kind, towards a more dynamic and more interactive applications. This is again from this Mars project, where geologists annotate, do their annotation on a reconstructed Mars surface, which has been brought to by the recent Mars missions. So what we found here is that we kind of struggled a lot, because we went all this visualization path, and then the interactions came in, and we crashed the curve, and we had a lot of complexity there. So the question here is, where does this complexity come from if we do 3D graphics applications with a lot of interaction? So what we basically have is, we have an application state, and we map this to the scene graph, which then ends up with the visualization. If something in the application state changes, we get the visualization updated because of this incremental system, which was introduced before. So this is fine. But what's getting more crazy is if you have user input, you feed it back, you get it into the application state, and you get some kind of callback held there by managing your application state. But of course, I mean, this is not new. This is totally known also for normal use application, use interface applications. So in that case, we took a step back and looked, okay, how can we improve our interactive 3D graphics applications, keep in there high performance, but have a better approach to interactive applications. And this is where we just went away and thought about, let's look at all those Elm-style applications. Looks rather simple. Why not going this way? So the question here, which came up, was, how can we do something like this in high-performance 3D graphics? And there are different takes on this. let us first investigate what are the challenges for this. What we have in 3D applications is we have super high frequency updates. For example, if you have an application where the camera moves through a virtual scene, you have super high frequency updates on the camera. If you do immutable updates for this camera part, for example, you do a lot of diffing in the scene representation. You also have large arrays. You need to do a lot of diffing here as well, so you need kind of good diffing algorithms, but also, which is more severe, if your view functions are heavy. If in the view function you want to decide what do I want to visualize in the first place. The camera is here. It doesn't matter to render high quality objects in that area down there. So in the view function we want to dynamically decide what our visualization should look like. So we move more complexity into the view function. And another thing is all those low-level graphics programming requires a lot of in-place updates, and if you fail to do an in-place update on a huge GPU buffer, for example, you get stutters in your animation because data needs to be computed, transferred to the graphics hardware via PC Express, for example. So we looked at what we now do is we unfold the Elm loop and look at it from an operational point of view. We have the update function which generates a new model. Then we take this, feed it to the view function, we generate DOM, for example, and then we do the diffing. And we tried a different approach here. We have a new, let's say it this way, the new model is typically rather small because we're talking about entities in the world. The view function, the view result, on the other hand, is rather big. This is also the case for user interfaces, but for 3D scenes, you often have 100,000 objects in your view function, in your scene graph, which is produced here. So this is rather big. So the idea here was to take the model and compute the diff directly on the rather small model, and then only execute parts of the view functions which have been affected by the changes which have been detected in this early stage. So I have a little demo on this. So we are now focusing on this part here, how to run parts of the view function. I'll show you the application at first. What we have now here is the full aardvark rendering engine, runs in .NET, and starts up an Electron. So this is like a mixture of web and non-web here. We can look at it. This is Yeah, here we have our user interface, and what's interesting here is if we just select here this area, you see here we have this diff and here is the image inside, and we do server-side rendering for user interface and for 3D graphics in that setting here. So if we move the camera here, new images get transferred from from server-side rendering to our view. And it gets updated there. If we do a structural change, like here, we can switch the 3D models. And what's happening here is, if we look at the delta, which is happening here inside, we get direct update of those texts. You see, this is like you're used to this, right? What is interesting here is if we look at the code, we have a rather, let's look at the model. Our model has the camera controller state. This is like, where is the camera now? Additionally, we want to render boxes or spheres. So you have this union type here, and we have this in our model. And now what in normal Elmish or Elm style, we would have a view function where this model arrives each time something changes. In our setting, we have it different because the diffing has already been done to the model. So the model is now already incremental. How does this look like in the view function? If you look at the view function, there is a lot of stuff I might show partly in the future. But here we have our view function. Here comes something magic. This is the M model. This stands for mutable model. And this has all the diff results inside already. So what we have here is our model has a field which is called current model. This is the same name as we had in the original model, but this one is incrementally tracked. So we explicitly depend on the results of the diff model here and say, okay, we create an incremental text and we take the current model, map it via mod map, dependency aware mapping here, and if it's a sphere, we say switch to box. If it's a box, switch to sphere, and this button then gets updated in this way. If we look at the code which is generated, so we on the server side we generate JavaScript update code and send this over to the client. The client executes it and updates the DOM. So it all happens on the server side. And if we now click our button, we see that we end up with just updating the text input. And this is all done without diffing the DOM in any ways. It's just done by diffing the model and then attaching to some fields some dependent computations which are then triggered precisely at that point where they need to be updated. And this is particularly interesting if we go to 3D rendering. Here we have a node. Yeah?
Question. Could you go back a couple of slides? Switch 2 slides, just quick. So, just go there, because you've actually got the diff on the model as well, right? So you said you compute the diff to the model, but you actually, your model is one of these incremental data structures.
Yeah, we take the model as it is and generate an, we will see this is an automatically generated incremental model.
Right, right. Okay.
So,
all right, okay. We show that later.
But we can see this in a few slides. So this is, I think, what we have here. Just to have another word on this, we also have a computation expression builder for building together those incremental computations. We have here the combinator-based approach, which was on the first couple of slides, and here we have the computation expression builder version, which translates into the combinator-based approach. This is useful if you're writing bigger view functions. You have a lot of mod map and stuff inside. Also, if you're working with lists, we have special computation expression builders for list sets, maps, etc. And this is awesome because it's particularly interesting for beginners. They often don't even recognize that they are writing adaptive incremental code. It just works. And if you're not doing side effects, it really works.
So can I just check if I'm understanding this right? So
sorry?
Instead of running the full view function,
yeah.
You've got the model and you've got the previous run of that
yeah.
model into a view function.
Yeah.
And you've set it up so that it generates diffs into that view function. So you only have to run the direct paths that impact it. Is that right?
Yeah, we only run parts of the view functions which are affected by the change which has been computed in the diffing algorithm, which has been applied to the model.
Okay, and do you have to track dependencies? Or
yeah, we track dependencies. We track each mod bind or mod map implicitly creates a graph in the dependency graph and attaches the lambda to the edge.
Great, okay.
And there is literature on this. This is not from us, or the implementation. It's awesome and it's from us. But there's Umut Akar's PhD thesis from 2004 and a surge of research which came after this, and we compiled all this research into our production quality implementation.
Incremental library as well.
Sorry?
Jane Street have a library called Incremental.
Your incremental library, you mean?
Jane Street, no camel.
Ah, yeah.
Yaraminsky.
Yeah.
Similar
Yeah.
to this. Do you think it's possible to take this part of what you've done and just make it the standard in Elmish? I mean,
yeah.
all of the MVU implementations suffer from the problem of really good.
Yeah. We did this partly, or we did it mostly, but in an experimental setting, yeah.
Yeah, I mean, this should just be the F-sharp standard way of doing incremental
Yeah.
computations, at least on the UI side. It's great. Yeah, it obviously works. And been tested, road tested.
Yeah, I mean, this is.
We would use this in Fabulous straight away.
There are some strings attached we need to talk about, but
there aren't that many. Yeah, I know there are.
what we have here.
Some increased difficulty in loading.
What we have here is semantically this is a push-pull based system where we push the dirty values and then we pull again, and this is based on this Hammer's work, or we did it at the same time as Hammer did, and the API here is from Monads for incremental computation from I forgot the name. It was a ICFP paper. Yeah.
I mean, but the key thing is you've road tested it so extensively. You guys are clearly building real world stuff with this, and so it seems like it's got properties that we need to make it the standard way of doing it.
Yeah, we could extract it in a simple form. This one also is thread safe, and yeah, it's we have a concurrency.
It doesn't guarantee consistency, but it doesn't get stuck.
Yeah, we have a kind of concurrency model behind it, but this is like.
So that means you can handle updates coming from. What does that mean?
You can multiple threads can pull and push into the system without the system getting stuck, but actually guaranteeing consistency. For example, if you just subtract A from A, or A from A will work, but if you have two cells and both contain 2 and you subtract them from each other and you change them, we cannot guarantee that the result is always 0. You might see intermediate results. It will eventually be correct, but not.
We do not have strong software transactional memory guarantees here, but actually we tried. And there were experiments in that setting.
I used to work on casino games, so if you would use this, would you get in trouble? Like, would it show a different number, maybe intermediate, but could that be possible? Like, you win random, would it show a different number because you have like an intermediate result?
Most often, if you at least we can make it work. You can always make it work by structuring your dependency graph in a way that it works, but it's actually
for consistency we need to think about it.
Consistency, no, it's always consistent as long as you use it single-threaded. So, or if you can also have one thread that pulls values out and another one that pushes them in, that's also okay. But if you have multiple changes from various threads, we actually thought about making that possible, but the runtime implications were just too hard. Because you kind of need to lock entire dependency trees and stuff, and there is no efficient way of locking an entire graph in one step.
There is some theory. I think this is kind of a theoretical stuff behind it, which could be explored better than we did yet. Because at some point, this is actually the story of the talk, that we make it simpler and but. Yeah. So now we looked at this part, running parts of the view function. Let's now look at it how we compute a diff. And this is I just give a rather simple code example. If we have just this example, we have an object which has a position and a name. We have a scene. The scene contains the camera position and a list of objects. What we now generate, this is as you will see, this is a compiler task. We did this is a pre-processing using F# compiler services. But this generates a type with the same name, except for M prefixed, also for the fields, whereby in here we push in the incremental data structures. This way we make it syntactically correct. And
what if V3D itself could be made incremental?
Yeah. I left this out for, but it works recursively, yes. And you need this. Normally, you would have an M object here as well. And this generated thing here would be an M object, and here we would have an A set or an A list, and then everything is taken care of. The A list is taking care of structural changes within the list, and value changes within the objects are taken care of by this by the other one.
And you got a list that's like an F# list. Have you got an A array as well, or is an A list?
A array is not that interesting, but A list is interesting. A list is super complex. This is we have in there. It's a lot of tree data structures whereby we maintain the indices for the list.
Yeah.
So it's like a functional array from that perspective, within some nice properties regarding prepend, append, and access.
If you insert into the middle of the list,
Yeah.
for example, you'll get a good diff on that.
Yeah.
If you insert 5 different places in the list, you'll get a good diff on that.
Yeah.
It's actually an implementation of a functional array, the base type.
Yeah.
It's an order maintenance data structure within slightly extended the chart map, where you can jump to a position in logarithmic time and just insert in a map.
Yeah.
And due to the order maintenance, you can always invent an index between two indices.
There's Tarjan et al.'s order maintenance data structure, and we have a simple version of that implemented in our base libraries in F#. There are some dragons in there as well, but
So, I mean, I know, kind of looking at your website, I know some of what you do is AGPL license, but if you could make this core part.
this is MIT.
It's all MIT.
Actually, it's Apache. Yeah. So what we basically do here is we just traverse the old scene and the new scene in parallel and check if something has changed. If we try to implement this, we have our old scene, our new scene, we have our mutable scene, and then we walk over the data structure and just flush the new values if they have changed into the mutable representation, and then the incremental system takes care of it. Huh? Ja, das kommt noch. So just to continue on this, this is, as you have seen it, we have this update function which takes a new model and produces unit, and the side effect marks all data out of date if this for the affected parts. We have this boilerplate, and here we have the F# compiler service based plugin which goes from here to here, and we have this integrated in the MS Build steps in our in our projects, and this way you never get distracted by this, but actually you are. So this is a part for this question and for the demo.
If type providers could take types as arguments, you could just use the type provider to do that transformation.
It actually worked if you put the types in a different assembly. You can load it.
So this is now a different demo. What we wanted to see is the generated file actually, right? This is the generated file, and here we have the M model. This creates fully qualified things, and that's it. Here's the update function. Yeah, never look at this. Hopefully the compiler is correct. Yeah, sorry, this is we have a Suave web server in the background, and we have fixed port numbers, so it didn't work with two applications started at the same time. What we have now here is, this is an example where we fly around. We have the similar example than before, but now we additionally have interactions on 3D data. And this is actually where it starts getting interesting from an application point of view, because we have the same approach for user interfaces as we have for 3D data. So they belong together and they have the same principle behind it. So we are kind of over time. So I'm gonna show you the results here. or how it is implemented. Or let's first start off with the model. It's always interesting. Forget about this. This is for Andorido. We have the camera state, and here we have a plist of positions. Plist is again a special data structure where we can look inside and generate efficient deltas or changes, can compute the changes efficiently. And here we have our update function. We get the model, the message. If the message is add a sphere to a particular 3D coordinate word space, we add this, we prepend this to our list. So this list gets updated here by prepending to the old spheres. Forget about this one, sorry. I didn't clean it up here. We just take the old model and replace the spheres. Let's look at the view function now.
Yeah, so is that the incremental? That one works on the model, not an M model.
Yeah, the update function needs to work on the model, so it's nice.
Okay.
And
Works on
we want to have simplicity of immutable data.
the M model is the actual mutable.
Yeah, the M model is just for view function and for doing the hard computations, and the logic should stay in purely functional immutable world. That's the beauty, actually. And here we have the view function, which takes the M model, and here so down there somewhere I create the scene. This is what Georg showed us before. This is actually just creating a scene graph, a sphere which is green and has size something, and I closed it, unfortunately, but this is the green sphere we had in the middle. And here is this FShade shader thing. We can inline say, okay, we want to have transformation and we want to have lighting on our sphere. So here everything comes together. We have incremental system coming together with FShade and scene graphs. And this again is our green sphere. And now we want to implement the interaction of clicking on the sphere and creating new spheres on the surface of the sphere. And this is beautiful because here we can, as we do for button on click events, we just say, okay, we have this scene graph. We additionally add an on-click event for this scene graph, which then, if clicked, fires add sphere, as for buttons. But in the background, it's slightly complicated, but because for clicking on 3D objects, we need to create this array into the 3D scene, intersect this ray with the objects there, compute the coordinates, and then call this function here, and then feed it to the Elm loop.
Signature on-click function.
Of what function?
On-click.
On-click. It takes v3d, this is our vector data type, and creates a message. And forget about this rather complex side here. This is our type for scene events. This should be actually hidden behind a type alias. However, interesting here, this with events takes a list of things which could be done to it.
And what is the connection between model and the messages? So how do you know that here is the correct message for this particular model?
We actually went a different way than Fable. We do not have a specific emit function that emits the messages. Our graphs and UI is generic type.
Okay.
It returns the messages, so to speak.
This is the original Elm.
Style. Which gets a little tedious with all the generic things. Yeah.
But it's awesome, actually. I think it's awesome because we have a bigger project where they use a lot of this programming style, and they always know what messages get produced in what parts of the application. And this gets particularly interesting when you nest view functions and compose together stuff which works in order to get stuff which works again. And if you know what messages get produced, you always tag the messages with the right context. Like in UI map in Elm, and here we have SG map. But it's not here in this talk, it's too much here. But just to have, I need to conclude here at some point. We have here our incremental data structure. From the P list, we created an A list. The A list can be listened on, so to speak. So we take the spheres we create by clicking, we map them by creating new spheres. Same approach here. And here the awesomeness starts because we can just do this. And that's it basically from the demo. So this brings me to this kind of summary of what happens. We have our model type, which is generated to a mutable model. We have our view functions, which depend on this M model by tracking dependencies, and then we fire back the actions or the messages and handle them in the update function as before. And this is kind of the generic message thing here. People are using this a lot. And this brings me to the lessons learned with this. It's contained in the aardvark media library. It's a bad name, but now it contains all this Elm implementation stuff. And what we saw is that it's hard for beginners to start, but after 2 days they're done with learning this incremental data structures, and they just use it without thinking about it. But it's not a problem because they are only using map and computation expressions builders, and handling the change and computing the changes or doing the logic behind is all done by the Elm logic and the incremental system, which powers this whole stuff. So the incremental system really makes this usable, and we used it in many projects. This is again this Mars project. Whereas this is really, they did a great job. They moved from a complete object-oriented crazy world to purely functional aardvark media-based approach. And this brings me to the conclusion. So there are some web pages. The open source platform, Aardvarkians. We have for research, we are always happy to have contributions in this. We are this. And we also have our startup, and on GitHub you have Aardvark platform with a lot of repositories, including Aardvark base, has most of this stuff I just talked about. That's it. From do you want to add something?
We're already over time.